Hello, my name is Jeff Schmitz, and I'm here to convince you that the universe is not expanding, that we have a steady state universe, and that there is not need for an expanding universe, and this actually fits in better and uses physics that's more standard. So, how a steady state universe can work using standard physics and why it's better than expanding universe. And as I said, it's my goal to convince you of this. So I'll list current problems with the expanding universe, Big Bang, explain redshift using gravity instead of Doppler effect that we have with the Big Bang, explain microstructures, or macrostructures, I should say, of the universe, explain the formation of galaxies from old black holes, eliminate the need for dark energy, and show that there are cycles to our universe. There are, well, like I hinted at before, old universes, that the remnants of that are all around us. So the problems with the Big Bang, the horizon problem, that's everything's very uniform as we look out in the distances. There, uh, universe is same at distances greater than light can travel for the known age of the universe. And so how does that, how do we have a solution for that? Well, we have uh, this inflation due to the grand unified theorem. As I said, a little bit of exotic physics that's still being worked on. Let's try not to use that. Clumping of the universe. So one thing is showing why the universe is so uniform. The other thing is saying, well, it's not that uniform. It's clumped. We're here. Galaxies are here. How does that happen? Well, dark matter. Well, I feel that we have a way of eliminating most of dark matter and all of dark energy. Voids and uniform densities. So galaxies, when you look into deep space, galaxies should be closer together. You don't see that. And also we see these voids, places where there seems to be no galaxies. Why is that? So this is showing roughly the idea here that there are clumps of galaxies and voids. There's another picture showing that, and also showing that there's really not a severe increase in the density of galaxies as we look further in the distance. Now that could be due to not being able to see them as well, but we should have some indication here. So this is an artist's conception of the macro structure, let's say, of our universe, where we have these filaments, groups of galaxies and lines like that, and voids, looking like, to my eye, like a sponge. Why is our universe looking like a sponge? So the Hubble constant, you look at the Hubble constant, and instead of the Hubble constant should be going faster in the early universe and slowing down, but that's not the case. We see that the universe it started out slow and speeding up. Why is that? Well, as I said, this is not a redshift due to Doppler effect, is what I'm saying. We see the galaxies are fully formed a lot earlier than we thought possible, and we also see these galaxies are forming around these supermassive black holes, and we're not really seeing these supermassive black holes forming. That should be a big event. So gravity can also cause redshift, just like the Doppler effect, and there's no need for expansion. Supermassive black holes are remnants from a previous universe. I'll talk more about that. So there's no need for dark matter, or not as much need for dark matter. Time restarts at random points. This explains the voids in the sheets with intersecting time bubbles, let's call them. So this whole idea was this is May of 2025, and I started thinking about this back in the beginning of March of this year. And the more I think about it, the more it fits in with everything that we have. So one of the things, I started thinking about this. I said, well, couldn't it be gravity that's doing this? That you start out with the universe that has a certain amount of mass to it and a certain amount of energy, and this mass gets converted into energy. Mass has gravity, energy does not. Now, electromagnetic radiation, let's say light, interacts with gravity. It's bent by gravity. Light can go and impart momentum, and momentum can be imparted to light. And of course, mass is also attracted to other mass due to gravity. That's not what I'm talking about. What I'm talking about here is it possible for light or electromagnetic radiation to be attracted to other electromagnetic radiation due to gravity? Does gravity couple between electromagnetic radiation? And the answer is no. I mean, look at something like the Maxwell's equation. We don't have a gravity term in that. And also, if gravity was with light, where is that? You know, since it's a massless particle, it's traveling at the speed of light. If it had some gravity to it, when it's coming towards us, we wouldn't, experience that gravity. When it's past us, we wouldn't experience that gravity. It's a massless particle. And so mass has gravity, and electromagnetic radiation does not. Anyway, so we go and we look at Z. This is the lengthening of the background radiation due to um, this redshift of the background radiation. We have it at 1,100. That's the how the wavelengths are being stretched. So Z for a point mass, we go and that's going to be we end up with this term that's a square root of 1 over r like that. But this isn't a point mass. What we're talking about, you think of this more like a sheet. And so this is a shell of this mass of the old universe that we see. We look 14 or so billion years ago in the past, and we have a denser universe. And this denser universe is the shell all around us, and we have that gravity due to that shell. And so we think that's more like you would like with electrostatics, like parallel plates instead of a point. And so this is building up. Not much, but we're talking about billions of light years. And so I get that. So I think of this as a sheet, and think of it as having a area density to it, and that area density ends up uh, around that, which is uh, um, 9 times 10 to the negative 6 kilograms per meter squared. And so we can think of this as like a um, our meter here, and we think this is like a long tube. Okay, and then how long of a tube are we talking about? So this is a meter square here at the end, and we have this x here. How long is that? And it's just throwing various numbers around. So like if we have like lose like half the density, or for instance, we have that the cosmic microwave background radiation is at 4.2 times 10 to the negative 14 joules per meter cubed. And if we look at that, that ends up around like 2 times 10 to the ninth light years. Okay, but then, as I said, you have this Doppler effect of a thousand, so that cuts it down. So we end up with something around, maybe around 2 million light years, this shell. Mass to energy. So what happens here is that we have an old universe, former universe, let's say, and what happens? All the stars die, and we end up with what's known as heat death. There's no more useful energy, nothing to run a clock. If there's nothing to run a clock, there's no more time. Nothing that can possibly, any sort of thing that could be used as a clock could not be used. Therefore, we cannot have anything, mechanical clock, even chemical reactions, things like that, would not happen at that point. So we we go and we get undefined in time. Time essentially stops, and then time restarts somehow. And we get these time bubbles, and we have most of the small black holes have evaporated, but the large black holes are still around. And so when we have the new universe forming, we still have these old supermassive black holes. So the idea here is that any object has some gravity to it. The Earth, a stone, something like that, is in a gravitational potential well. Our sun, and essentially what we are at is we're in a potential hill because we look at the universe in the distance. At the old universe from 14 billion years ago, it's a lot denser, and so it's in a gravity well, let's say. We're at the top of this, so we're essentially like a potential hill all around us. Um, uh, so all around us, we see that the things are redshifted, and this isn't the uh, yes. Most of this mass turns to energy at the very beginning of the universe, but it's still continuing right now as we speak, and so that's why we have this change. So it appears like uh, like we have this change in redshift, like the universe is getting um, moving faster and faster, and really it's just the redshift is uh, gravitational redshift is going in this nonlinear fashion. And so what do you need to run a clock? As I said, you need a heat source and a heat sink. We can't run a clock on gravity waves. It'd be hard to run a clock on neutrinos. And so, as we said, we get a cold universe, everything's the same. We sort of lose track of time. We also think of this as um, a very uniform energy level. Imagine a universe without time. And then, for whatever reason, we have these sparks where time decides to start again over a vastness of space. And when it does, we have this soup, this stuff that had been separated into matter and energy, and it becomes this matter energy soup again, and the matter sort of comes out of the energy and antiparticles and all that, and this region of time expands out at the speed of light. And we have several of these, and they expand out, and eventually they hit into each other. And when they do, we have this interface. We have these supermassive black holes that are more or less evenly scattered around this area, and we have galaxies that nucleate